I wanted to look at dose rates. It's one of the most commonly misused and misunderstood concepts in this hobby. So what is a dose rate? Well, dose rate is a way of measuring how much damage radiation is doing to the human body. And the higher the energy of the radiation, the more damage it does to the body, yielding a higher dose rate. But some detectors cannot tell the energy of radiation. And if you think about it, that could be a big problem. So they assume the energy of the radiation. So say I'm using a detector like this. This is a Geiger counter. It's a Geiger-Muller tube inside here. So this counter is one of them that assumes about the energy of the radiation. Say we're measuring this sample. This is americium-241, which, in case you don't know, emits very, very low energy gammas. This detector does not know it emits low energy gammas because it thinks that it is actually the isotope that it was calibrated against, because it has no way to know that it's not. It has no way to know that it's americium. So it's going to believe that it's the isotope that it was calibrated against, which is, in most cases, cesium-137. Cesium-137 has a much higher energy than americium-241 that we are actually measuring. Remember, higher energy radiation does more damage and has a higher dose rate. So if this thinks that it's higher energy, it's going to think that it's a higher dose rate than it really is. The same thing can also happen in reverse if you set it up the opposite way. Say you're trying to measure a really high energy isotope. Well, the counter's still under the impression that you're measuring cesium, but really there's a lot more energy and it's doing more damage, so the dose rate should be higher, but the counter has no idea. So how do we fix this? Well, there's two solutions. You can either use a whole different type of detector, or you can use a GM with a filter element. This device right here is called the Radii G10, and in the back, right in front of the GM, you have what's known as an H*10 filter. Don't worry about the H*10 part, that is far beyond the scope of this video. But basically, it kind of flattens out the curve, if you want to look at it that way, of the over response and the under response. But if you want to use a different type of detector, that might be even better. This is a scintillation detector. They can tell the energy instead of just flattening it out, which is known as spectroscopic compensation. Basically what that means, it knows you're measuring americium, not cesium, so it can adjust the dose rate likewise. Now, just to solidify this and hopefully help it make a little bit more sense, we're going to do our own little experiment. All we're going to do is we're going to take these two counters. This one is energy compensating, which means it has the filter inside of the meter, so it's not over responding or under responding. This meter is just a GM, no filter. We're going to look at two sources. This is the low energy americium source we looked at earlier. With the G10, we're going to just leave it here for a minute. And it looks like our peak value was 0.37 microsieverts per hour. That is the max it went to. Let's see what this one goes to. 1 microsievert per hour. Definitely an over response there. Now we're going to look at the cesium source. This is the isotope that they were both calibrated against. This meter is going to assume it's cesium, and it is cesium, so it should be accurate here. But to be fair, cesium emits some betas, so we're going to put this coin over it to block those betas so that we can get a fair estimate of only the gammas. Around 5.5 microsieverts per hour. Also around the same value. It's been Nigel from Alpha Gamma Physics here today, and I really hope you enjoyed this video and found it helpful. Be sure to leave a like, subscribe, hit the bell, share this video with anyone you think might like it, and leave a comment if you have any questions or suggestions. Thanks for watching.